Welcome to Organic Chemistry. This video will focus on alcohols. Let's get started. In IUPAC naming, alcohols outrank alkenes, alkynes, and halides. Why? Because oxygen is more oxidized than carbon. Therefore, naming priority follows oxidation state. Alcohols use the suffix -ol, so number the chain to give the alcohol the lowest possible number. Only if that number is identical from both ends do you then need to worry about alkenes, substituents, or anything else. Above, we review the previous methods to make alcohols from alkenes. There's also an SN2 substitution that we learned where an alcohol can be generated from an alkyl bromide being attacked by hydroxide. Below, we see oxidation states in review. Here, we need to stop memorizing and start counting. Oxidation states are not just a fake bookkeeping. We treat with oxidation states ionic covalent bonds like ionic bonds. And here we can clearly see that the more carbon bonded to hydrogen bonds we have, the polarity is inverted towards carbon, and the more reduced the structure is. Versus the more carbon single bond to oxygen bonds we have, the more oxidized we have. And so that's why methane is essentially gaseous gold, and carbon dioxide is so problematic because it's so damn stable. With this oxidation and reduction spectrum in mind, we return to sodium borohydride as an excellent reducing reagent only for reducing acid chlorides, which are extremely reactive, and the carbonyl of aldehydes and ketones in order to convert these to alcohols. Again, notice how in all of these mechanisms, the polarity of that boron to hydrogen and aluminum to hydrogen bond is drawn towards the hydrogen, and it's the polarity of those bonds that sync up to the carbonyl and allow for the hydride to be formed with the carbon, and that pi bond to be formed with boron and aluminum. But sodium borohydride is really not as strong as lithium aluminum hydride, and lithium aluminum hydride can reduce acid chlorides and carbonyls of aldehydes and ketones, but it can also reduce the esters and carboxylic acids to alcohols. In the opposite direction, we begin with the Pinacol rearrangement, which historically was one of the first ways chemists were able to turn alcohols into carbonyls, and not being a form of oxidation. Really, it was a rearrangement. It starts with two carbons at the same oxidation states, and it ends with unequal oxidation states. Still, the sum is equal. So it moves the atoms, not the electrons. So this is not a redox reaction, but it is most definitely noteworthy. Clearly, there is a need for effective oxidation states, and historically enters chromium 6. This oxidizing agent is very effective, but extremely ugly and obsolete. These reagents most definitely work, but they work too well. Jones oxidation oxidizes a primary alcohol right to a carboxylic acid. Secondary alcohol, therefore, they form ketones. Okay, and there's no control here. These are also carcinogenic, environmentally are disastrous, um, and unfortunately they persist in curriculum because of inertia and not because of wisdom. Modern chemistry has most definitely moved on. Uh, PCC, pyridium chlorochromate, would have been the later version of this chromium-based reagent, and it was able to oxidize primary alcohols into aldehydes and secondary alcohols into ketones. However, these reagents should be noted as being extremely dangerous, hazardous, carcinogenic, and not used now in modernity. Of course, learning those chromium reagents is not useless information. We can learn from the sins of our past. And Swern oxidation, Des-Martin oxidation, these are the more common, most common oxidation of alcohols to carbonyls. In Swern oxidation, sulfur does the dirty work, and entropy is driving the reaction. Chromium is out. And in Des-Martin oxidation, hypervalent iodine does the oxidation, and it's clean and precise. Again, however, you're not wasting your time learning the chromium reagents, because you should see and notice in the mechanism that at the end, you notice that the alpha hydrogen elimination step is essentially all the same. And so being familiar with these mechanisms allows us to learn from them and adapt into the future. We now turn to the halogenation of alcohols. Honestly, these mechanisms should not look new. We first encountered these under the substitution reactions when we introduced substitution and elimination. Uh, Towards the end of that video, we encountered using sulfuric acid and dehydrating alcohols in the presence of sulfuric acid to produce alkenes. If you remember, that would function by elimination reaction and using heat. We also showed how we could use HBr, so same processes that we see here, and produce alkyl halides. The problem is these reactions really do compete with each other, especially under heating. And this reaction is particularly slow. So really, we're going to expect that of these reactions, only perhaps the last one, for tertiary alcohols where rearrangements are unlikely, that this would be a preferable method, but definitely not under heating. And this leads us to much more selective methods for the halogenation of alcohols. Enter phosphorus tribromide. This proceeds by SN2 attack. There is an inversion and no rearrangements. This method is ideal for converting primary and secondary alcohols into alkyl bromides. It is most definitely driven enthalpically by forming stronger, more polar bonds. And in the contrast, to form alkyl chlorides, not alkyl bromides, but alkyl chlorides, we use SOCl₂. It follows a similar logic. It's driven by SO2, sulfur dioxide gas formation. And pyridine controls the acidity. And in this process, it is driven entropically. Tosylates return as we consider alcohols and wrapping up their reactions. They're extraordinary in terms of control. If we want to convert the alcohol into another functional group, an excellent method is to convert the alcohol into tosylate and do an SN2 with any nucleophile that we want. Tosylates are resonance stabilized, inductively stabilized, and they are most definitely spectator ions that leave beautifully. Alcohols really are a point of departure in our narrative of organic chemistry. We have shifted away from talking about alkanes and alkenes and alkynes. We have now built upon the framework of substitution and elimination, and now we're really diving into reactions that provide interconversions between functional groups. Till next time, Crip.